Hello, my name is Abdeslam Polarius. I'm an assistant professor at Rutgers University, and I will be talking about model identification for robotic manipulation. Welcome to my talk. So this will summarize a little bit my work that I have been doing in the last 5 or so years. So if we look into humans in general, they are able to manipulate objects very easily with very high dexterity. And robots are still very primitive in this sense, so they cannot do anything remotely close to that. And the end goal of my research is to eventually enable robots to achieve the same high level of dexterity and ability to manipulate objects. And actually, baby humans, they can learn already to grasp objects and use them around 4 months already. And this is not special to humans, but apes in general, they can use tools, and this is all very well-known fact. And I think the next step in evolving robots is to enable them to achieve this kind of same level of dexterity. This is not surprising because if you look into the human motor cortex, you will notice that actually a big part of it is dedicated to just controlling hands. And given the high level, the high number of degrees of freedoms that we have in our hands. And the kind of manipulation tasks that I'm looking into here are these kind of experiments where you have an object that is completely unknown to the robot, and the robot picks it and may hand it to another robotic arm and then insert it in some location. This is work that is under review for a RAL submission that we did this year. I want just to make a quick distinction between the work that we are doing and the work that is being done in classical industrial robotics. So typically in industrial robotics, you have objects that are known, they have known properties, they are placed in highly structured environments. We have very precise and dynamic models of robots. And in intelligent robots, usually we are talking about robots inside households or inside workshops where the objects are unknown. They have unknown 3D shapes, they have unknown poses, they have unknown friction coefficients, masses, and all this is known to the robot. Additionally, the objects are placed in structured and uncertain environments, and the robots have inaccurate and complex dynamics models. So solution to all that is, I think in my opinion, is learning from experience. So collecting data, and then from that, the robot will be able to complete all the information that's missing. So this is the first work that I did on grasping. That was a while ago, 2012. That was with my colleagues Oliver Kommer and Jan Peters, and that was done at the Max Planck Institute, where the idea there was we collected point clouds of objects, and then we provided labels where it's good to grasp the object and where it's bad to grasp the object based on a simulator that's called GraspIt, and provided labels, and then used a machine learning tool called Markov random fields, and that tool allowed us to generalize to new objects, as you can see in this video. So given a completely new object, we can generalize from the data that we collected in simulation. That was the very first thing, and then later on I started looking more into grasping objects in clutter. And here this is an experiment that I did in 2014 where we throw objects in front of a robot, and the robot is tasked with clearing clutter and grasping all objects from there. So this wasn't very challenging, it turned out, not as challenging as I thought at the beginning. And solution to that we proposed back then was to, in simulation, take images of objects and then label each point and each orientation of the hand if this point is good for grasping, if the grasp is going to be successful. You take all that data and then you put it inside some function that you train. That function can be used to generalize to new scenes where you have a new pile of objects, and then this function will give you heat map that indicates at each point what would be the probability of succeeding at grasping at that location. So of course, this is pretty standard these days by using, for example, neural networks, but that was done in 2014, which is, I think, one of the earliest works that were performant at such level of complexity. One thing I noticed was that the answer that you are getting from the neural network is not going to be, of course, optimal, and the grasp that will be suggested by neural network is going to be a little bit far from the optimal grasp. So what you need to do is you cannot trust directly the output that you get from learning, but you want to verify it in simulation. You want to collision check and check the stability of the grasp. So the idea is that you get the best suggestion from learning, and then you want to fine tune it in simulator by locally changing and playing with the rotation of the hand until you come up with the best grasp. And the way we do this is by using Bayesian optimization, which is actually quite standard tool, and basically Gaussian process that gives you a distribution from which we can conclude distribution on the optimal grasp, or distribution that you know so far. And we propose an idea which is called greedy entropy search, where we have this distribution of the optimal grasp, and then the next grasp or next action that we want to try is the one that contributes the most to the entropy of that distribution. So the x that has the highest contribution to the entropy would be the point that you want, the grasp that you want to test and try next. And this gives us an anytime search method where, given enough time, you can converge, the error gets smaller and smaller, and you converge quickly to the optimal solution, and you can stop this process whenever you run out of time. And the proposed method, greedy entropy search, outperformed some standard approach which was called entropy search actually. So this is a variant of it. And of course, both of them are better than just doing greed search. So I wasn't very excited or impressed by the experiment that I did before, where we just do clutter clearing, because there was enough space between the objects. You can always find a way to insert fingers around an object and grasp it. And the objects were kind of moving around also a little bit easily, so you try to grasp an object and you push away another object. So I thought of building a setup where the objects are close to each other and you cannot really grasp them immediately. So we have these wood pieces that are actually taped to the table and they cannot move. And in order to grasp these objects, the robot needs to push the pipe, for example, into the front, or push the box, and so on. So we need to include now pushing actions that would facilitate the grasping, that would create enough space, separate objects and create enough space for grasping. So you need to manipulate the scene before you'll be able to grasp the objects. So this becomes a sequential decision-making problem where you have sequence of pushing actions followed at the end by grasping action. And a typical approach would be to just use standard model-free reinforcement learning, where you learn from trial and error, you apply actions, you receive rewards and observations, and from that the agent can, or the robot can learn what would be the best strategy for combining pushing and grasping. So following this approach, so first thing we need to do is to define a reward function, and in this experiment the reward function would be you get positive reward whenever the robot manages to grasp something. And this can be computed by the robot itself by looking into the angles of the fingers as it's trying to squeeze something. It can tell if it succeeded to pick something or not. And anything else, pushing, failing to grasp, anything else is just given negative reward or 0. And then I used this kernel-based reinforcement learning, which is kind of glorified weighted average, basically. So we have a state here is an image, action is grasping or pushing action. And we take the average over the data, weight them by how similar is the test image and test action with the images and actions that we have collected during learning. And this gives us the value or the quality of grasping action or pushing action, and then we can generalize to new scenes. And this video that shows this kind of experiment where the robot initially is just exploring. So this is using epsilon greedy exploration policy, where the robot is just trying a lot of random actions. And initially, they're not exactly completely random because they are aligned to the principal and secondary axis of the object just to speed up the learning. Eventually, by chance, it will discover the nice combination of actions that you have to perform to get those rewards. And it's still exploring, but then eventually it starts converging to just performing the optimal action over and over again. So this happens after convergence. It will just keep repeating exactly the same maneuver that it learned on its own autonomously. So this is a self-supervised system. All right, and this is also true if in the future I like all sorts of different rotations of objects that worked quite well. Then that was on those objects. Then I took exactly the same method and I tried to apply it on slightly more complex scenario where you have an object buried under rocks, for example, and the robot needs to learn how to pick up the hammer. There is a hammer that is buried under all those rocks, and the robot needs to learn how to do that. So it needs to learn what kind of rocks should I push and how can I manipulate this scene such that I can pick the object that is buried there. And this is using, again, model-free reinforcement learning, using exactly the same approach, and that was an epic failure. So it didn't work at all because the robot just went on exploring and exploring forever. And even after tweaking with exploration rate, we still didn't manage to make it converge to the optimal behavior. And the reason is because the high complexity of the image, basically, and if you push the objects a little bit, then the image will look like completely new. And if you have very little image, it's very difficult to generalize from just small number of images. So eventually it's still failing to cross per rock, for example, and it's still just exploring and exploring. So this was a failure. And this made me think about that this is perhaps not the right approach to solve this problem. And I think the right approach, and this is what I will be presenting in the rest of this presentation, is instead, and this was just, okay, pick the hammer, but that was just by chance there. And the right approach, I think, is to, given this scene, you want to infer the properties of the objects as you are pushing them. You want to segment, you want to learn their geometries on the fly, and you want to learn their mechanical properties such that you can replicate this entire scene in simulation using physics simulation, and you will be able to solve the problem in simulation to come up with optimal actions, and then you can execute it on the real setup. So the conclusion from there is models are very important, actually, and we want to learn models in real time on the fly and use them for choosing actions.